So, what is calculus? This isn't one of those things we inherited from the ancient Greeks like geometry. This subject was created more recently in the late 1600s by Isaac Newton and Gottfried Leibniz. They didn't work together. They both created calculus on their own, and as a result, there was a huge argument over who should receive credit for its discovery. Today, let's talk about what they discovered. In calculus, you start with two big questions about functions. First, how steep is a function at a point? Second, what is the area underneath the graph over some region? The first question is answered using a tool called the derivative. And to answer the second question, we use integrals. Let's take a look at the derivative, the tool that tells us how steep a function is at a point. Another way to think about the derivative is it measures the rate of change of function at a point. As an example, let's use the function f of x is equal to x cubed minus x squared minus 4x plus 4. Suppose we want to find the steepness of the graph at the point -1 and 6. How would we do it, and what do we even mean by steepness? In algebra, you find the rate of change of a line by computing the slope, the change in y divided by the change in x. But this is a curve, not a line, so we get a good look. Here's the idea. Pick a second point nearby. How about the point -8, -0.8, and 6.048. Next, draw a line to these 2 points. The slope of this line is a good approximation for the steepness of the curve at the point -1 and 6. If you compute the slope, you get 0.24. So what if we pick a different point that's even closer? How about -0.9 and 6.061? If you compute the slope of the line between this point and -1 and 6, you get 0.61. And we get a sequence of slopes which are getting closer and closer to some number. The lines are getting closer and closer to the tangent line, and the slope are approaching 1. So, we say the slope of the curve at the point -1 and 6 is 1. We call this number the derivative of f of x at the point where x minus -1. This is the slope of the tangent line to the point -1 and 6. In calculus, you will learn how to find a function that will give you the slope of any tangent line to the graph. This function is also called derivatives. So, next, let's take a look at the integral. This is the tool that lets you find areas under curves as an example. Let's look at the function g of x is equal to sine x. What if we want to find the area under this curve between x is equal to 0 and x is equal to pi? We know how to find the area of simple shapes like rectangle and circles, but this is much more curvy and complicated. Here is the data slice the region into a bunch of very thin sections. Let's start with 10 slices. For each section, find the area of the tallest rectangle you can fit inside. There are 10 thin rectangles. The width of each rectangle is pi over 10. And we can find the height using the function g of x. Next, up the areas of all 10 rectangles. We get a combined area of 1.66936. What if we do this again, but we use 25 slices instead? This time, we'll get an approximate area of 1.87195. Let's do this again and again using thinner and thinner slices. 50 slices, 100 slices, 1000 slices. You get a sequence of areas that are getting closer and closer to some number. It's look like the area is approaching 2. We call this area the integral of g of x from x is equal to 0 to x is equal to pi. So we have these two tools, the derivatives and the integral. The derivative tells us about the function at a specific point, while the integral combines the values of the function over a range of numbers. But notice there was something similar to how we find the derivative and the integral. In the case of the derivative, we found 2 points that were close to each other. Then, we let one point get closer and closer to the point that we're interested in. In the case of the integral, we took the curve and we chopped up it into a bunch of rectangles to approximate the area under the curve. Then, we took thinner and thinner rectangles to get better and better approximations. In both cases, we're using the same technique. In the case of the derivatives, we're letting the points get closer to each other. In the case of the integral, we're letting the rectangles get thinner. In both instances, we're getting better and better approximations, and we're looking at what number the approximations are approaching. The number they are approaching is called the limit. And because limits are key for computing both the derivatives and the integral, when you learn calculus, you usually start by learning about limits. A lot of your time in calculus will be spent computing derivatives and integrals. You'll start with the essential functions, which is the polynomials, trigonometric functions, which is the sine, cosine, tangent, exponential functions, and logarithmic functions. These are the building block for most of the functions you'll work with. Next, you will make up more complex functions by adding, subtracting, multiplying, and dividing these functions together. You'll even combine them using functions compositions. In calculus, there are a lot of rules to help you find derivatives and integrals of these more complex functions. The derivative rules have names like the product rule, quotient rule, and chain rule. The integral rules include U substitution, integration by parts, and partial fraction decomposition. When you first calculus, your focus will be on basic functions, function with one input and one output. So once you've mastered calculus for basic functions, you'll then move up to higher dimensions. For example, consider a function with 2 inputs and 1 output, like f of x and y is equal to e to the power of negative x squared plus y squared. Earlier, we compiled the derivative by computing slopes of tangent lines. But in the higher dimension, things are a bit more complex. This is because in a surface, instead of a tangent line, you'll have a tangent plane. To handle this, you'll compute the derivative both in the x direction and the y direction. We call these partial derivatives. These two partial derivatives are what you need to describe the tangent plane. We'll also need to generalize the integral, the region below a surface in 3-dimensional. It has a volume, not an area. To compute the volume, we'll approximate it using a bunch of skinny boxes. To sum up all the volumes, you'll need to use a double integral because the boxes are spread out into 2 dimensions, but don't forget, we live in 3 spatial dimensions. So you also need to learn calculus for functions with three inputs, which is the y, x, y, and z. If a function has three inputs and one output, we call it a scalar field. An example would be a function returning the temperature at any point in space. And the outputs of functions don't have to be simply numbers. They can also be vectors, the function with three inputs, and, a vector output are called vector fields. An example would be a function that gives the force vector due to gravity at every point in space. To recap, the two main tools you learn in calculus are the derivatives and the integral. The derivative tells you about a function at a specific point. Namely, it tells you how quickly the function is changing at the point. The integral combines the value of a function over a region. You'll start your study of calculus by learning how to compute the derivatives and integrals of a wide variety of different functions. And you'll learn a lot of rules to help you. That's all. My topic is all about